Hello world, we are April the 16th, 2024, and today I would like to make a YouTube episode demonstrating the validity of the proof regarding the Syracuse or Collatz conjecture, or at least make an attempt, and I hope to push it online before June. Please forgive my French accent and my falsely Irish nickname, but my pseudonym should not mislead you. I would like to make a scientific publication, but I don't know how to do it. And when I contact organizations, I generally don't get an answer. As I am not a mathematician, I will invoke my right to be wrong, and I still hope that what I have to publish will be worthy of a scientific interest. In order to introduce myself a bit more, you just need to know that I have been working independently on the topic for maybe 15 years. I was fond of chaos theory, and I was curious about what is known as the Syracuse sequence in France, or the Collatz conjecture, or the 3x+1 problem. As I am not a professional mathematician, I do think outside the box, and I hope the point of view of an unknown science fiction writer will help the true mathematicians to finally prove the conjecture. Because today, I'm not completely sure to convince everyone. Or maybe I will use a conjecture to prove the conjecture. I will also use some French notations, or my own ones, and I hope you will follow my reasoning. So, in a few words, what is the Collatz conjecture or the Syracuse sequence? If you have an odd number, you multiply it by 3 and you add 1. If you have an even number, you divide it by 2 and you go on. Well, the conjecture just think that at the end, if you pick any seed number, you will end on 1. And always a cycle afterwards of 4, 2, 1, 4, 2, 1. You may wonder if there is a kind of counterexample or another cycle, but definitely not. I will just prove that there is only one cycle and no reason to look for another cycle or another number that could not converge towards 4, 2, 1. In some other YouTube videos, you see YouTubers picking example of numbers like 5 going to 16 and 8 and 4 and 2 and 1. I will not do this. I will just straightforward go to abstract numbers. And I will detail something that for me is a common mistake that is made by many mathematicians when they are considering a kind of compressed sequence. They think that an odd number is multiplied by 3 divided by 2 step after step. This is a main mistake. It takes 2 steps. Okay, this is obvious, but it's good to remember because my reasoning will include probability, and in terms of probability, it will be important to not make a confusion between what is happening after 1 step and after 2 steps. I made the mistake, and this is the reason why it's good to learn from the mistake and correct the model that you are using to make sure that you understand fully what is happening in this Syracuse sequence. So in the first part, I will just develop the mistake I have done trying to simplify the Syracuse sequence and to prove the Collatz conjecture, and then I will develop the true model. In the first time, I wanted to check if the Syracuse sequence was doomed to be increased and increased towards infinity, or if it has a chance to fall towards 4, 2, and 1. So instead of focusing myself on what was happening on u index n plus 1, I decided to take into account u index n plus 2, because this way we can merge what is happening to odd and even numbers. and it is 3 divided by 2 multiplied by u index n plus something, and it will happen 75% of the time, whatever is u index n as a seed number. You can remember I try to demonstrate the validity of the proof for any integer, positive integer. So what is happening the other 25% of the time? Well, you've got all the integers that are divisible by 4 and are still integers. So it's u index n divided by 4. What can I do with this? Well, an expected value, which is a kind of probabilistic average, and any gambler can know this. It is just a kind of average of the statistic gain of the Syracuse sequence. So on the second rank, when you iterate the Syracuse algorithm, you have an expected value that is 1 point something like 18 and 75 multiplied by u index n to evaluate roughly u index n plus 2. So the Syracuse sequence is increasing. Of course, you have fractional remainder, and I will talk about it later on. It has its importance, but so far you can ignore it. It is just to give you a feeling about the paradox that is so hard to solve. The Syracuse sequence is increasing, but its limit when you iterate the algorithm is going down towards 4 to 1 and then 4 to 1. So how come? So I decided to iterate again this algorithm for u index n plus 3 and n plus 4, and it was pretty easy. For the rank number 3, so u index n plus 3, if you try to evaluate its expected value, well, you have 3 scenarios, and I insist on the importance of having scenarios, because depending on the seed number you pick, you will have a different behavior of the Syracuse sequence. So in the first scenario is for me the maximum scenario. You will always choose in this one that your seed is probably an odd number and will meet, it's a kind of probability language, but it will have on the rank 3 2 odd and 1 even on its path. So if you try to evaluate u index n plus 3, it is 9 above 2 multiplied by u index n plus epsilon 1, a kind of fractional remainder, and I don't want to know it for now. And it has, or it should have, this is what I have thought in the first attempt, about 37% chance. 37.5, because of course half of the first scenario on the rank number 2 will be divided by 2 because they are even, and the other half is of course odd and will be multiplied by 3 plus 1. Okay, second scenario, it's 3 above 4 u index n, and then you've got another fractional remainder, and the third scenario, so the minimal one, is u index n divided by 8, because these are the integers that are divisible by 8. Okay, so far so good. You can calculate again an expected value, and it is slightly above 2. And something was happening in my mind, and it was crap. This Syracuse sequence is increasing too much, but it is not increasing as fast as you can expect. If you consider a geometric sequence, and the geometric sequence should increase even faster than this. So in fact, this was the first light of hope, because when a sequence starts to grow slower than it should be, you might manage to demonstrate something. Okay. So I iterate again the Syracuse algorithm for u index n plus 4, and then we've got again 3 scenarios. 9 divided by 4 multiplied by u index n plus a fractional remainder. 3 divided by 8 multiplied by u index n and a fractional remainder, etc., etc. You have an expected value on average that is 1.52 or 53, depending on how you round this number. So it was encouraging because even rank was producing a smaller number. So I decided to go for 30 iteration, and I have this table, and unfortunately there is no point where the Syracuse sequence is going downwards. I still decided to map the expected value of the logarithm of the expected value against the logarithm of what it should have been if it was 3 divided by 2 elevated to the power of each n plus 2 iteration, because of course this 3 divided by 2 only happens for 2 steps of the algorithm, not 1. This is important. And here, with this kind of reasoning, you can just see that, yeah, the Syracuse sequence is increasing a bit slower than expected if it was a pure geometrical sequence. So what to do? I decided to roll up my sleeves and express the Syracuse sequence at each iteration of the algorithm without any approximation until something would happen. And it's a tedious work. So welcome in the second part of my video, and I hope I will not lose your attention because things are going even more interesting. In fact, the Syracuse sequence is so complicated that we always want to oversimplify it in order to understand how it works, and this is how we make mistakes. So, when I told you just before that there was on the number 2 rank, when you have iterated twice the Syracuse algorithm, you had 75% chance to have 3 divided by 2 u index n plus a fractional remainder that you didn't give attention. It was right and it was wrong. In fact, this 75% is hiding something different. It is not exactly a true 75%. It is just a 50% first scenario where you have 3 divided by 2 un plus a half, and it only happens when your starting number, your seed number, is odd, but something important happens when your seed number is even. Of course, you still got 3 divided by 2 multiplied by un, your seed number, but it is plus 1. And it took me some time to realize that this number was even. Because if it was not even, on the next iteration of the algorithm, you would find something that would be multiplied by 3 plus 1, and it cannot happen. Because no odd number is consecutive in the Syracuse sequence. So you have a kind of excess of even numbers, which are generated in the Syracuse algorithm. And it's the key parameter to understand the behavior of the Syracuse sequence. And this is an important point because if you consider the Syracuse sequence and the first scenario, it is even or odd. If you consider the third scenario on the rank number 2, it is even or odd. But the second scenario is fully even. So it's compulsorily even. So when you do this without any other kind of calculus, you have a kind of strange pattern that appears because you will consider then the Syracuse sequence as a kind of gathering between a sequence starting with odd seed numbers, and I will write them with an I for impair in French, and another Syracuse sequence starting with even seed numbers, and I will write them with an A, which is the second letter of pair in French for even. Okay, you can adapt in English if you are a native speaker. And now is the crazy thing. I will demonstrate that the Syracuse sequence is not increasing nor decreasing. It is a kind of stagnating sequence in terms of expected value, of course, statistic average. If you consider the IN sequence on the rank 0, when you do not have iterate your Syracuse algorithm yet, this will lead to, for all I index n, a kind of this will lead to a kind of composition that is fully odd. Then, if you iterate once the Syracuse algorithm, it will be fully even. Then half even and half odd. But of course, you take the 50% odd and you add half of 50% even. It makes 75% even and 25% odd on the rank number 3. And you iterate again, it is 62.5% even and 37.5% odd on the rank number n plus 4. And you go on, and of course something will start to take a shape in your mind when you see that on the rank number n plus 5, you have 68.75% of even numbers and 31.25% of odd numbers. And you have, when you are looking to the AN sequence, so AN is just the sequence of Syracuse applied to even numbers, you will find exactly the same behavior with just one step of shift. So you have exactly the same behavior, but not exactly at the same step. The even number Syracuse sequence is one step ahead, always one step ahead. But it's not a problem, because when you sum up these two sequences, you obtain the Syracuse sequence, and you can try to formalize a bit this excess of even numbers. I will note P index n, the proportion of even numbers in each subsequence. So P index n plus 1, so when you iterate the Syracuse algorithm, is equal to P index n divided by 2, because of course only half of the even numbers are divisible by 4. And I will add 1 minus P index n, because this is a proportion of odd numbers that are becoming even numbers when you are iterating the Syracuse algorithm. And guess what? The limit of this sequence of even numbers proportion is tending towards 2/3. So quite quickly, in almost 15 iterations of the Syracuse algorithm, you will have 66.66% of even numbers. So 2/3 of even numbers. The Syracuse algorithm is generating an excess of even numbers. And when you are calculating the expected value of such a sequence, you will multiply this 2/3 of even numbers by 1/2, because, well, they get divided by 2, and you will take the 33% of odd numbers, you will multiply them by 3, just to give you a feeling of the statistic average of the Syracuse sequence. So you take 2/3, it becomes 1/3. You take 1/3, you multiply it by 3, you get 1. 1 plus 1/3 is 1.33333 something. So it just means that after some iterations, the Syracuse sequence, U index n plus k, k is undefined, is just equal to the starting number, U index n, multiplied by 4/3. And that's all. And you just add fractional remainder to just have an idea that it is not exactly this expression, but it's just proving that the Syracuse sequence will never increase towards infinity in average. This is important. It is just proving that for any starting number, somehow, after any finite number of iterations, you will find again your starting number multiplied by 4/3 and with a fractional remainder that you are just adding. Just to make sure the theory was valid, I decided to iterate in exact way the algorithm of the Syracuse sequence, and I will spare you all the details, but I will just show you maybe some Excel screenshots to evaluate what we call in French espérance, for expected value. So in the rank number 2, it's still the same than before, but in rank number 3, it is only about 1.6, so the Syracuse sequence is increasing even slower than before. Then it is just below 1.3, then 1.5, then 1.35 at the rank number n plus 6, then 1.48, and for the rank number or index n plus 8, it is 1.38, something about, okay? So it's slowly converging towards 1.33 or 4/3. I cannot push forward the exact calculations because it is still simple in the rank number 1 or 2 because you just have 3 scenarios. But then the scenarios are multiplying. You've got 5 scenarios for the rank number 3. I guess you have something like 8 scenarios for rank number 4. For rank number 5, you have 13 scenarios. For rank number 6, you have 21 scenarios, or 21 cases if you prefer. And for the rank number 7, you have something like 34 scenarios. And for the rank number 8, 55. It's a disaster. And I foresee that for the rank number 9, it would be 89 scenarios, 89 cases, different cases, and different fractional remainder to calculate exactly. And it becomes very time-consuming for someone who is working alone. Why am I talking about scenarios instead of cases? Because I am a science fiction writer, even if it is an amateur one, okay? And for me, each case is a story that is happening on the seed number. It has its own path towards its convergence. And you remember what I have said, you have obvious even numbers and hidden even numbers. The hidden even numbers are in the undefined case, when you are just looking at an equation that defines a scenario, or a case if you like. You don't know exactly if it is even or if it is odd in advance. So when you are calculating the 2 different cases afterwards, on the next iteration, you've got to split the probabilities between the children scenarios of the n-1 rank, okay? It is only when you are sure that you have an even scenario, fully even, that you can give 100% of its own probabilities on the child scenario. Because of this, at each iteration of the Syracuse algorithm, your number of cases you have to consider is multiplied by around 1.66. So each time you are trying to calculate in an exact, accurate way the Syracuse algorithm, you will consider 1.65 more cases. And it's a nightmare because the number of cases to consider is exploding with iterations. So it just means that if I want to calculate 50 iterations of the Syracuse algorithm, I would have to calculate in an exact way 57 billions of cases. It's impossible. But this is not too bad. Welcome in my third party about this demonstration of the proof of the Collatz conjecture. And it is about finding a very destructive method to prove that this Syracuse sequence will tend towards 0 after some numbers of iterations. Despite all the appearances, the Syracuse sequence is not steady. And depending on how far or how close you look, you will have different conclusions. If you remember correctly, I was talking about scenarios for all the different cases you can imagine in terms of combination of odd and even numbers on your path of Syracuse. So now let's have a look on the maximum scenario. So I have written S1. S1 is an unlikely and perfect alternation of odd and even numbers and the worst case for the convergence of the Syracuse sequence. This worst case can be not easily but reasonably easily written as a sum of powers of 3 divided by a powers of 2. And I will put the equation on the screen. In fact, each time you increase the number of odd multiplication by 3, you will also divide the probability of having this number by a factor 2. So in terms of expected value of this maximum scenario, you have something like half power k iterations multiplied by 3 halves multiplied, at the power k iterations, multiplied by u index n, your starting seed number, plus a fractional remainder that I will express as best as I can. I'm not very gifted for this, but I hope that the mathematical expression is correct, and multiplied by a half factor elevated to the power k. And the more iteration you make, the more it will tend towards 0. So when you are looking at this fact, you will conclude that the maximum case or scenario of the circle sequence is tending towards 0. So if it is the maximum number of all the cases, all the other cases are also equal to 0 after some iterations. Not an infinity, but a reasonable number, something like 100, a bit more sometimes, because what I have written is an average, so you will always have an average, a standard deviation, and some errors. So it says the nickname of some numbers, like 27, that are hard to converge towards the cycle 4 to 1. 4 to 1, of course, that is the closest steady cycle close to 0, because the expected value of the whole circle sequence is now equal to 0. This is a bit brutal, because you do not expect this when you are looking at the circle sequence from an average point of view, when you are just looking at a few iterations. But the behavior of the sequence after not an infinity, but almost an infinity of iterations, or a huge number of iterations, reasonably huge for the average, is just tending towards 0. And this is another paradox, because how come this circle sequence, which seemed to be steady for a given parameter k of iteration, where it was steady in terms of expected value around 4/3 of its initial seed number, how come that then it is just collapsing towards 0 after some more steps? This is a mystery. This is a mystery, but I have some clues. And some of you that are more aware, or more mathematicians among you, will also stop me, saying, okay, the circle sequence tends towards 0, since its maximal case is also tending towards 0. But if the cases are multiplying, then you've got a sum of terms that is exponentially increasing, and then the sum of all these almost 0 terms is not tending towards 0, because you can change the equation if you tend to know what is the sum of expected values of all the scenarios. This is a way you can say it in English, and I try to make myself as clear as possible on this topic, which is not easy. Well, this sum is not tending towards 0 if the scenarios are still multiplied by 1.66 or 0.65. They are not enough even numbers. So something must happen to increase with more iteration the ratio or the composition of even numbers inside the circle sequence. How do they get to 66% to maybe 80% to have a steady circle sequence, or even more than 80% to make it collapse towards zero? And welcome in the fourth part of my video, where I try to burglarize the solution. In fact, my intuition was a picture. I had the feeling that I was a kind of thief who was turning the buttons of a safe, waiting for the right tick who would indicate that the safe would be opened. In fact, each time you make an iteration of the circle sequence, it's like turning slightly the button and trying to know what will happen next. It's like a rotation without being a rotation of these buttons. To make myself clearer and end the kind of comparison, I looked at some scenarios where the sequence was a bit different. It was scenarios where you start with an odd number, for example, and then you meet an even number, and an even number, then an odd number, even, even, odd, even, even. So it means one number and two even number. With this kind of ratio, you have another kind of scenario in terms of fractional remainder. And this is the reason why it is important not to neglect any term in the circle sequence, because when you are making some infinite sums of this fractional remainder, you have something pretty interesting. For this case, you've got 1 divided by 4 plus 3 divided by 16 plus 9 divided by 64 plus 27 divided by 256 plus many things, and I will express the general term. And guess what? This sum is tending towards 1 in about 50 to 60 iterations. So it means that in that case, a kind of undefined scenario is tending towards a fully even scenario, or a scenario full of even terms. So it just means that this way, when you do not neglect any term in the iterations of the circle sequence, you can prove that a scenario that should be mixed or undefinedly mixed of even and odd numbers is in fact probably full of even numbers, and when it's full of even numbers, it's divided by 2. So the multiplying factors of 3 does not apply anymore to 50% of the child scenario, but to 0% maybe. This would be my guess, my own conjecture to demonstrate the Collatz conjecture. I cannot honestly do it for the 57 billions of scenarios and cases that exist downstream of the first iterations. And my apologies for this. Someone will have to do it. A true mathematician with a powerful computer. And I'm just able to guess the correct form of fractional sums depending on the scenario that will tend toward 1 and which are able to tend towards 1. And I guess that in maybe 50 to 100 iterations for an average of 100 numbers that I have tested, or probability number, a kind of density of, not a density of probability, but for probability of number, yeah, this will be true. So it means that The Syracuse sequence has to be studied in terms of probability and expected value. And when you consider this expected value, it will tend towards an odd number plus 1. The fractional remainder can become 1 after some iterations. Maybe the results are very close between what is an odd number and an even number, but it explains why suddenly, after dozens of iterations, instead of being volatile around an average that is steady, the Syracuse sequence is collapsing slowly. And this works. I mean, when I try to compare experimental figures, picking some numbers between, in my experiments were just the 200 first integers, and then I shifted to 2000s or more until 1 billion, and it works so far because Excel is able to calculate with this kind of numbers. But then with bigger number, I don't have the computer to make the calculations. Anyway, it just proves that, it does not prove, it is just a conjecture so far, but it is a strong one. You have a high probability to prove that for many structures of almost infinite or finite sums of fractional numbers of powers of 3 and 2, you can make them tend towards 1. And then you can make the shift between the 60% of even numbers in the Syracuse sequence to more than 80%. And then it means that the coefficient of the expected value is less than 1 in the multiplication in each iteration. So this is explaining the mechanism that will bring towards 0 any number, any seed number where you have started through the algorithm of Syracuse. Of course, it does not prove that 421 is the convergence cycle for any number, but since it should be 0 in average, there is no other cycle. We have founded one, so okay, congratulations, it exists, but there are no other one. It's not possible, in fact. So my method, that is a probabilistic one, does not foresee this cycle of 421, 421. But it's obvious it cannot be another one, because when you are reaching 1, 3x plus 1 is the only case when a multiplication by 3 with an addition of 1 is like a multiplication by 4. So come on, it's useless to look for another cycle. So this is the end of the video, and I hope that you are convinced now, or almost convinced, or interested by this attempt to demonstrate the validity of the proof of the Collatz conjecture, or the Syracuse conjecture. And I'm waiting for your comments. I truly hope that this video will help the most mathematicians of you, and that it was useful and interesting. Maybe this video is just the proof, but I'm not completely sure that you will accept it. But if it is true, please share it and always remind where you have found the proof of the Collatz conjecture. It will be the end of more than 80 years, I guess, of research to find a solution of the 3x+1 problem. For many English speakers, it will be useless to subscribe. You can just like or comment. I am ready to, of course, answer your comments. And all my other videos are in French, so it's just, for science, not for making a promotion or any kind of thing. I guess it will be my only video about mathematics.